The next family of organic compounds we're going to look at is the halogenoalkanes. Now, like alcohols, the halogenoalkanes can be classified into primary, secondary, and tertiary. And this is important to understand the types of reaction that they're going to go through. But it's the exact same as with alcohols. So a primary halogenoalkane, like the first one here, primary carbon, is when our carbon is only attached, so our carbon that's attached to the halogen, here we're using chlorine, is only attached to one other carbon. That makes it primary. When the carbon attached to our halogen is attached to two other carbons, it's secondary. And when the carbon attached to the halogen is attached to three other carbons, that makes it a tertiary halogenoalkane. Okay, and again, this is important because the primary, secondary, and tertiary, certain ones undergo one type of reaction and the other ones undergo a different, which is what we're going to jump into. The type of reaction that we have for halogenoalkanes is called nucleophilic substitution. Okay, we're going to break this down and what all the words mean. We already know substitution is when we replace one thing on a molecule with another thing. Nucleophilic substitution is we're replacing something with a nucleophile, which we'll get to what that is in a moment. So nucleophilic substitution converts a halogenoalkane, okay, into an alcohol. So that's the overall process. So a halogenoalkane, say chloromethane, for example, can be converted into methanol. So the carbon, here we have an example of chloroethane. So we have two carbons, CH3, CH2, and a chlorine. So an important thing with these reactions is the carbon here on the carbon-halogen bond. This is a polar bond, right? The electron density is being pulled toward the chlorine, leaving the carbon partially positive and the chlorine partially negative. Now the partially positive one is the one we're interested in because the fact that this is partially positive makes it attracted to electrons. So other molecules which have free electrons, for example, I'll just draw a generic molecule here that has a lone pair of electrons. These lone pair of electrons are going to be attracted to that partially positive charge, and that's what allows this reaction to take place. This species that is attacking the positive carbon, this is what we call the nucleophile. Why a nucleophile? Because it's what are in the nucleus of atoms, but positive charges. So it's things that are attracted to positive charges. That's what a nucleophile is, or something that's attracted to the nucleus of another atom. Okay, so a nucleophile, we call it a nucleus-loving species that's attracted to positive charges. So nucleophiles will have either a full negative or partial negative charge, making them attracted to the partial positive, and they'll also have a lone pair of electrons, which they use to perform an attack. Okay, the one we're going to look at is the hydroxide ion, OH. Right, if we draw it out, we have our OH. There is a negative charge on the oxygen, and it has electrons, which it can use to perform the attack. So we're going to examine these as used as nucleophiles, which will create our alcohols. Okay, so a substitution reaction takes place where a halogen atom is displaced by the hydroxide ion. There's two examples here. Let's look at the first one. So we have our halogenoalkane. In this case, we have 2-bromobutane. Okay, and we add our sodium hydroxide. The alcohol here, or the OH, the hydroxide, is going to substitute and replace the bromine, giving us our alcohol. So butan-2-ol, or 2-butanol, whichever you want to call it, and sodium bromine. The second example, same thing. Here's our halogen. We have a chlorine, which is going to get replaced by our hydroxide ion once it performs that attack with its electrons on the carbon. And we get our alcohol and our sodium chloride, or our salt. The conditions you need for this is you have to have an aqueous base. So in this case, we're using sodium hydroxide. It's a strong base. And it has to be heated up. Okay, so it can occur at room temperature, but it will be very slow depending on what halogenoalkane and what you're reacting and what base you're reacting. So generally, heat is applied to make this go a little faster. Okay, and again, we call this a nucleophilic substitution because the halogen is being replaced by the nucleophile, which is the hydroxide group in this place, to produce an alcohol. Now, there's two different types of nucleophilic substitution depending on what classification of halogenoalkane we have. The first type is an SN2 reaction. Okay, so what SN2 stands for is bimolecular, hence the 2. So bimolecular nucleophilic substitution, hence the N for nucleophilic and the S for substitution. So again, bimolecular nucleophilic substitution reaction. Why bimolecular? Because two molecules, okay, are involved in the rate determining step. When this reaction happens, two molecules are moving at the same time. In the reaction, we use curly arrows to show the movement of pairs of electrons. So let's put our pair here on the hydroxide. We have our negative hydroxide. We have our halogenoalkane. I'm going to fix that pair of electrons there, make that a little better. There we go. So we have our pair of electrons. The hydroxide, being negative, is attracted to the positive carbon. So what happens is this pair of electrons, okay, attacks the carbon, forming a bond between the carbon and the oxygen. Now, carbon can only have 4 bonds. So as this one is attacking, the halogen bond is leaving. Okay, so this bond is breaking, and the bromine will leave. So we call this, because the hydroxide is attacking from the opposite side, and this will always be true for SN2 reactions, the hydroxide is attacking from the opposite side of the halogen, we call this a backside attack. When we get into some more advanced organic chemistry and start looking at stereochemistry, we'll come back to this and examine some specifics of what happens. But for right now, I'm just going to give you the name backside attack because it's from the opposite side of the halogen, and it happens, the bond is made at the same time the halogen bond breaks. Okay, so in this process, we have a transition state where this bond, our OH, is in the process of forming, and the Br bond is in the process of breaking. So this whole state, you'll see the square brackets around it, has a negative charge. Essentially, the OH here is like a half negative charge, and the bromine is also a half negative charge. So the overall is a negative. Then finally, once we get to this state, once it's in this state, the activation energy has already been reached, so the reaction will just continue to happen. The OH bond will form, and the Br bond will break. Okay, and we form our alcohol. Okay, again, this is an SN2 reaction. Now, an SN1 reaction is our other type. So this we call a unimolecular nucleophilic substitution. Unimolecular because only one molecule or one atom is moving at the same time, which means that's the only one that's involved in determining the rate of reaction. So the first step in this involves a heterolytic fission. Remember, that means that both electrons are going to one atom. So it involves a heterolytic fission forming a halide. So this bond, before the hydroxide comes in and attacks or anything, this bond breaks. Okay, and both electrons go to the bromine. Now the reason, well, actually we'll get to the reasoning why in a second, of why it's SN1. So this bond breaks and it becomes a Br minus, which is just off now in the solution. It leaves the carbon with a full positive charge because we've lost an electron off of the carbon. The bromine took both within the bond. So now the hydroxide ion, the OH, again with its lone pair of electrons, can now attack that positive charge as it's a nucleophile and attracted to it. And it will form our alcohol. Okay, so just like the other ones, a halogenoalkane to an alcohol, it's just the process is slightly different. So the attack by the nucleophile in this case is incredibly fast because it's attacking a full positive charge now, but it does require this first step to happen with the bromine breaking, which is a fairly slow step. Now, what makes one type of carbon undergo SN2 versus an SN1 reaction? Okay, and that depends on their classification of primary, secondary, or tertiary. So I'm going to draw I'm going to just circle the positive carbon in each of these cases, or the partially positive carbon, okay, attached to our halogen group. So this is the carbon that would be being attacked in each case. Okay, primary halogenoalkanes predominantly undergo SN2 reactions. So here's the bromine. Our hydroxide would come in from this side, its lone pair of electrons, and attack from the opposite side of the bromine. With a tertiary halogenoalkane, the problem is there's too much of what we call steric hindrance. Okay, so steric hindrance basically means there's a bunch of other stuff in the way. So this hydroxide can't actually get in to attack because these other methyl groups here, here, and here are, oh, remember, these things aren't just stationary. They're constantly moving. So they're moving, they're swinging around. The hydroxide can't get in to attack that carbon. It's blocked. There's too much hindrance in its way. So again, we call it steric hindrance. So what has to happen first is the bromine has to leave, okay, with the bond breaking and the electrons going to the bromine. Then it leaves this other side, once the bromine's gone, it leaves this other side completely open for the hydroxide to attack. Okay, so a tertiary halogenoalkane will undergo SN1, and again, a primary, where there's lots of room, will undergo SN2. A secondary halogenoalkane generally undergoes a mix of SN1 and SN2. It depends on some other factors like the solvent it's being done in, the temperature it's being done at. We're going to look at some of these again later once we do the more advanced section of organic chemistry. But for right now, you just have to know that it could be either at with a secondary halogenoalkane. Let's take a look at a couple of examples and do some drawings. So the first one, name and draw the mechanisms for the following substitution reactions using NaOH as the nucleophile. So we have bromoethane. Okay, so bromoethane, we have our carbon, 2 carbons because it's ethane with a bromine off of one of them. So again, I'm just going to draw the skeletal structures for these. So we have our bromoethane. We have our this is a primary halogenoalkane, it's only attached to one other carbon. We have our OH, which has its lone pair of electrons, its negative charge. It's going to be attracted. Again, this carbon here is partially positive charged. The bromine is partially negative charged. These electrons are going to attack the center. The bromine is going to leave. And we undergo, so remember in this case, it goes through a transition state, okay, where we have the bromine bond in the process of breaking. We have the hydroxide bond in the process of forming, and the overall state has a negative charge. And then when it comes out the other side, we have our ethanol formed, plus our Br minus. Now remember, in this whole case, we have sodium ions floating around, balancing out these negative charges that we show. So bromoethane, being a primary carbocation, primary halogenoalkane, undergoes an SN1 or SN2 reaction. So I'm going to repeat that. The molecule here we have is a primary halogenoalkane, so it's undergoing an SN2 reaction. So our next example is 3-chloro-3-ethyl-pentane. So we have pentane, which is 5 carbons. On the third carbon, we have an ethyl group and a chlorine group. So in this case, we have a tertiary halogenoalkane. So the hydroxide cannot attack. There's too much steric hindrance from the back, so it cannot do its backside attack. So the first thing that happens is this bond breaks, and the electrons go on to the chlorine. Okay, and it forms our carbocation intermediate. So this carbon here has a full positive charge, and we have our chlorine up here with a negative charge. And we have our hydroxide, which is going to then replace the chlorine, so it's going to attack the positive carbon center here, resulting in our alcohol group. Something to note here is that if we start with a tertiary halogenoalkane, we end up producing a tertiary alcohol. So in the previous example, let me go back for a moment. In the previous example, we end up forming a primary alcohol. In this case, we could actually take this primary alcohol, it's just a little extension, and using the oxidation method we learned in the last lesson, we could oxidize this alcohol into a carboxylic acid, for example. So we could go from bromoethane all the way to ethanoic acid. Whereas with a tertiary halogenoalkane, when we produce this alcohol, it's stuck here. We can't oxidize this any further because it's a tertiary alcohol. Okay, so this is it for nucleophilic substitution reactions. So again, we had our SN1 and our SN2 reaction. There's a lot of information here, a lot of drawing our mechanisms with our curly arrows. Make sure to review, try to practice a couple of these problems. And the last video we're going to see for these functional groups next time is on benzene.